Hey everyone, welcome back to Chem Story. Today we're diving into a key concept, one that's super important for understanding SN2 reactions. It's called nucleophilicity. Ever wondered why some nucleophiles work better than others? That's exactly what we're going to explore today. In SN2 reactions, there are four major factors that affect how smoothly things go. First, the nucleophile. It's the one that starts the attack. Second, the substrate. Its structure controls how easy it is to reach the carbon. Third, the leaving group. If it leaves easily, the reaction goes faster. And fourth, the solvent. It can help, or it can get in the way. Out of all these, the nucleophile is the real MVP. A strong nucleophile speeds things up. A weak one? It slows the reaction down. Maybe even stops it completely. But here's the thing. Instead of memorizing which nucleophiles are strong or weak, it's much more useful to understand what makes a nucleophile strong in the first place. So today's focus is nucleophilicity, what it is, what affects it, and why it matters in SN2. We'll talk about the other factors, like leaving groups and solvents, in a later lesson. But once you understand nucleophilicity, the rest will start to make a lot more sense. Alright, so what is a nucleophile? It's an electron-rich species that looks for electron-poor places, like an electrophilic carbon, to make a bond. In an SN2 reaction, that bond-forming step happens in one go, so having a strong nucleophile is critical. But here's the catch. It also has to be small. If the nucleophile is too bulky, it has trouble reaching the carbon. That slows down substitution, and it might push the reaction toward elimination instead. So the big question is, what actually makes a nucleophile strong? Let's break it down. First up, charge. In general, negatively charged nucleophiles are stronger than their neutral versions. Why? Because more negative charge means more electron density, and that means a stronger push to donate electrons. Take hydroxide. It's much more reactive than water. Same goes for alkoxides versus alcohols, or amide ions versus ammonia. The pattern's simple: more charge, stronger nucleophile. Next up, electronegativity. Less electronegative atoms make better nucleophiles. Why? Because they don't hold onto their electrons as tightly, so they're more willing to share. Take atoms in the same row of the periodic table. Carbon is the least electronegative, so the methyl anion is super strong. Then comes the amide ion, followed by hydroxide. And at the bottom, fluoride. Fluorine holds its electrons too tightly to be a great nucleophile. You see the same trend in neutral molecules too. Ammonia is better than water, and water is better than hydrogen fluoride. Let's talk about polarizability. This is about how easily an atom's electron cloud can shift or stretch. The more polarizable it is, the more flexible it becomes. And that makes it a better nucleophile. And that's why halide nucleophiles get stronger as you go down the group. Iodide is the most polarizable, so it's the strongest nucleophile. Then comes bromide, then chloride, and at the bottom, fluoride. It's small and rigid, so it's the weakest of the bunch. Now let's see this in action. Starting with fluoride, it's tiny. It holds onto its electrons really tightly, so its electron cloud doesn't stretch much. That's a problem in SN2. In the transition state, good orbital overlap is key, but fluoride can't align well with the carbon's orbital. That makes the transition state less stable, with higher energy, so the reaction slows down, or might not happen at all. Now let's look at iodide. It's much bigger, and way more polarizable. Its electron cloud is soft and flexible. That makes it easier to line up with the electrophilic carbon. So the transition state becomes more stable, which lowers the energy and helps the reaction move faster. That's why iodide is a much better nucleophile than fluoride in SN2. Its polarizability really boosts the reaction speed. Let's talk about bulkiness. Even a strong nucleophile can struggle if it's too big. SN2 reactions need a backside attack, and bulky nucleophiles just don't fit well. Take methoxide and tert butoxide, for example. They're both strong bases, but methoxide is small. It slips in easily and makes a clean attack. Tert butoxide, on the other hand, is bulky. That bulk gets in the way, so even though it's reactive, it doesn't work well in SN2. Now let's talk about solvents. They play a big role in nucleophilicity. Before we look at how they affect SN2 reactions, here's the basic idea. Solvents fall into two main types, polar product and polar aproduct. Polar product solvents, like water, alcohols, amines, and carboxylic acids, have OH or NH bonds. That means they can form hydrogen bonds. Polar aproduct solvents, like THF, DMF, acetone, and DMSO, don't have those bonds, so they can't form hydrogen bonds with nucleophiles. Got that? All right, now let's see how these two types affect reaction rate. Let's start with polar product solvents. These can form hydrogen bonds with nucleophiles. That stabilizes the nucleophile, but it also slows it down. Why? Because of something called solvation. In polar product solvents, these solvent molecules surround the nucleophile, forming a kind of shell, and that shell gets in the way, making it harder for the nucleophile to attack. Here's the key point. The smaller and more highly charged the nucleophile is, the more tightly it gets solvated. Let's take sodium bromide in water as an example. The sodium ions, Na+, are surrounded by the negative ends of water molecules, and the bromide ions, they're surrounded by the positive ends. That's solvation, and it helps stabilize the bromide nucleophile in solution. And here's why that really matters. All halide ions have the same charge, but they come in different sizes. Smaller ions get more tightly solvated. So when we compare halides, we can clearly see how solvation affects nucleophilicity without other factors getting in the way. Now, here's the key point. Larger halide ions are less tightly solvated, and that makes a big difference. When solvation is weak, the nucleophile stays more exposed and more reactive. That's why, in polar product solvents, fluoride, the smallest halide, is the least nucleophilic. But iodide, it's much larger, so solvent molecules can't surround it as tightly. That leaves it free to attack, which makes it a much stronger nucleophile in SN2. Now, let's flip the situation. What happens in polar aproduct solvents? Unlike polar product ones, these solvents don't strongly interact with anions, so nucleophiles don't get trapped in a solvent shell. Instead, they stay exposed and ready to react. To see how this works, let's take a look at sodium bromide in a polar aproduct solvent. Let's take NaBr and acetone as an example. In water, the Br- ion is heavily solvated, and that really slows it down. But in acetone, it stays mostly free. Na+ still interacts with the oxygen atoms in acetone, but Br- doesn't get pulled in the same way. That means Br- remains exposed and reactive, making it a strong nucleophile for SN2 reactions in polar aproduct solvents. Now here's something interesting. In polar aproduct solvents, nucleophilicity actually follows basicity. Smaller anions are stronger bases, and here, that makes them stronger nucleophiles too, so the order flips. Fluoride becomes the most nucleophilic, followed by chloride, then bromide. And iodide? It's the weakest in this case. Why? Because polar aproduct solvents don't stabilize the nucleophile. They leave it exposed, free to act on its own. So in this kind of environment, the stronger the base, the stronger the nucleophile. Let's see how solvent choice affects nucleophilicity by comparing SN2 reaction rates in different solvents. First, take methanol, a polar product solvent. In methanol, iodide is the most reactive, and fluoride is the least. That's because iodide is large and loosely solvated, so it stays free to react. Fluoride is small and tightly solvated, and that holds it back. Now switch to DMF, a polar aproduct solvent. Here the trend flips. Fluoride becomes the most nucleophilic, and iodide drops to the bottom. No hydrogen bonding means less solvation, and that's why nucleophilicity now follows basicity. But what if we keep the nucleophile the same and just change the solvent? Let's say we're working with bromide. In methanol, it's heavily solvated, so the reaction moves slowly. In DMF, it stays mostly free and reacts much faster. The result? SN2 reactions run significantly faster in polar aproduct solvents like DMF because they don't get in the way. They let nucleophiles do their job. Now let's go over some common nucleophiles in SN2 reactions. They can be negatively charged or neutral, and their reactivity depends on things like charge, electronegativity, and solvation. Most nucleophiles contain atoms like oxygen, nitrogen, carbon, halogens, or sulfur. These types show up all the time, so it's good to keep them in mind as you study SN2 trends. Let's compare how different nucleophiles affect SN2 reaction rates. The data shows a clear trend. Nucleophilicity increases as you move down a group on the periodic table. Ions like hydrosulfide and cyanide, they're highly reactive and give fast reactions, but neutral species like water, much slower by comparison. So what's the key takeaway? Charge makes a big difference, and the atom behind the nucleophile? That matters too. Both play a major role in how fast the reaction goes. But reactivity isn't everything. Some nucleophiles are also strong bases, and that means substitution and elimination can compete. So to predict the reaction pathway, you've got to ask, is it acting more like a nucleophile or more like a base? That distinction matters. It tells you whether the reaction goes SN1, SN2, E1, or E2. To make that easier, we can group reagents into 4 main categories based on their nucleophilicity and basicity. Let's start with type A. Strong nucleophiles, strong base. These reagents are highly reactive, and they can take part in both SN2 and E2 reactions. So what determines the outcome? It all depends on the structure of the substrate. If the carbon is easy to access, SN2 is favored. But if the substrate is bulky, E2 takes over. Some classic examples include sodium hydroxide, sodium methoxide, and sodium amide. All of these come from very weak conjugate acids, with pKa values typically above 15. That means they're not just nucleophilic, they're strongly basic too. Now on to type B, strong nucleophile, weak base. These guys love attacking electrophiles, perfect for SN2 reactions, but they're not strong enough to pull off a proton, so they don't really push E2. Some typical examples: iodide, bromide, thiocyanate, cyanide, alkyl thiolates, and acetate. Type C, weak nucleophile, strong base. These guys are bulky, and that bulk makes it hard for them to attack carbon directly. But when it comes to grabbing protons, they're great at it. That's why they favor E2. Some common examples include potassium tert-butoxide, lithium diisopropylamide, and strong, non-nucleophilic bases like DBU and DBN. Last one, type D, weak nucleophile, weak base. These don't initiate the reaction themselves. They wait for a carbocation ion to form first. That's why they're suited for SN1 and E1 pathways. Common examples include water, alcohols, and neutral amines. They don't push the reaction, they follow it. So what's the big picture? SN2 needs a strong nucleophile, E2 needs a strong base, and SN1 or E1. They happen when both the nucleophile and the base are weak. We'll dig deeper into these pathways later on. But for now, just remember this: nucleophile or base, that choice sets the whole reaction path. When it comes to nucleophilicity, energy matters. A good nucleophile sits higher in energy, and that makes it more reactive. A poor one is lower in energy, so it reacts more slowly. Let's take a look at the energy diagram. A strong nucleophile starts at a higher level, so it doesn't have to climb as far to reach the transition state. The activation energy is smaller, and the reaction goes faster. But a weak nucleophile starts lower. That means the energy jump is bigger, and that slows the whole reaction down. For a fast SN2 reaction, you want a high-energy nucleophile, one that isn't too stabilized by solvation or resonance. Let's wrap it all up. Nucleophilicity depends on 5 main things: charge, electronegativity, polarizability, bulkiness, and the solvent. In polar product solvents, big polarizable ions like iodide work best. In polar aproduct ones, small basic ions like fluoride take the lead. We also saw how nucleophilicity connects to base strength and activation energy. Bottom line, a strong nucleophile is fast, available, and fits the reaction conditions. Up next, we'll break down how the substrate, leaving group, and solvent affect SN2 reactions. See you in the next lesson.